Today we have with us Dr. Abhishek Narain Singh, basically a biological engineer, he has a toward computation biology. He has rich experience. He visited hundreds of places in the US and Brazil. He will be talking more on the analytical techniques of data mining techniques related to genomics and related fields.
Thank you, Professor Shari, for a humble introduction. My name is Abhishek Singh, and the talk, as you see, is bio data analysis in a big data perspective. So these days we talk about a lot about next generation sequencing technologies. So let's start with that. So why analytics is important? When we talk about analytics, we talk about the scientific models, the statistical models that we build, and then we try to do the operation for a huge data. So there are two-way algorithms we approach. One would be the statistical algorithm for the serial component. The another algorithm is a parallel component. How we divide our work, how we separate, distribute our work. For that, there is a combination of approaches that are being used. So R is become very popular statistical tool for doing statistical modeling, and OpenNPI is the message passing interface, which is openly freely available, that is being used widely. There are various versions of NPI, LabHPI, NPI CH, and other things. And instead of R, people also use SAS, SPSS, many more tools like that are being used commercially. But these two are freely available, so I'm announcing that. So the importance of informatics for the health industry is, if I want a number that can tell why it is important, then the most important number is going to be the money number. The number which tells us how important they are is shown by the millions of dollars of money that is being poured in terms of research grants and the promotional activities that is there. Say for example, by National Institute of Health in the US. For human genomes, there's about $2,000 million, and for age research, there is like $2,500 million. That's the amount of money that is being poured in every year, and that is, the number is increasing. That's the amount of money that is being poured in to show the importance of why these researchers should be funded and supported. So we talk about personalized prescribed, personalized medicine because we want that there should be a shift from a reaction to prevention, because we want a more accurate diagnostic of the individual who is suffering from a disease or can be a positive agent for a disease. There should be a predict. We need to have a tool to predict the susceptibility for the individual to a disease, to improve his health, and to know the disease progression. So we talk about the DNA-seq, we talk about the RNA-seq. I am pretty sure all of you guys are aware of these things, so I'm not elaborating more into these details. But that's where the research is progressing, and day by day the sequencing, the technology of the cost of sequencing is reducing down. We want a more customized disease prevention strategy, and to reduce the time, cost, failure of pharmaceutical clinical trials, eliminate trial and error efficiency that inflate healthcare costs, and undermine patient health. So SNPs, I'm pretty sure everyone knows of it, single nucleotide polymorphism. They have been found to be associated with many kinds of diseases, either directly, indirectly, or possibly associated. So there is already a lot of work that has happened associating single nucleotide polymorphism with autoimmune diseases, cancer, genetic diseases, neural diseases, cardio diseases, and psychological traits, right? Digestive disorders, female-specific disorders, addictions. So there has been a lot of work already that has gone into science and the database that has compiled a lot of information that is kept through over a century or several decades that people have carried out research, and this database is there by either in a distributed fashion or in a common database, which we need to mine and make use of. So some of the sample SNPs are, for example, say this disease. We know that this is the loci of, this is the ID given to the SNP, and these are the SNPs associated with it. And we also know the P2 region P and the Q lobe of the chromosome, where it tells about where which region it belongs to, and the chromosome number where it is found. So coming to data mining. So for data mining, what we do typically, and we have been doing like subconsciously, if you're into bioinformatics, first thing you learn about is sequence comparison. You have a query sequence, you have a subject sequence, and you compare the two sequences to see how much homology exists between the two sequences. And you set up the kind of parameters to see how much mismatches are there. You put a penalty for that. How much matches are there, you put a score for it. How much gaps are there, you put a penalty for it. And then for gap extensions, you put a separate penalty for it. There are open source software for this, but I wouldn't name any of them because I don't want to advertise anyone in particular. But there are many open source software that does a lot of these things. But you as a bioinformatician has to be careful as to which one is the one that will be suiting your data. That will be getting you the information that you want. Right? So based on that, you build up the model, you test it on a sample data of your choice, see what you're getting is what you expected for those for which you know the results already. And then after that, you get a Poisson distribution like this. And based on the Poisson distribution, you get high scoring pairs. And those high scoring pairs with scores above a certain cutoff, you select them and filter them. And there's a p-value and n-value, you put a statistical number to it. And this whole model is then subjected and fired to the data using MPI, or these days Hadoop is also very popular if you know Java. And if you don't mind a bit of the time complexity to be reduced, if you do in C programming, it's pretty fast. In Java, it becomes slow, but then it depends on how comfortable you're happy in handling which programming language. So one of these tools I made was Genome Brick, which does this whole parallel programming work using MPI, OpenMPI, and a statistical modeling work for, say, the whole genome. There's about 3 billion bases on X and Y axis both. So you have the Celera company's reference genome and the NCBI reference genome on the Y and X axis respectively. And the matches and mismatches are color coded over here. The higher the percent for the matches, I'm putting it red, and the lower matches are put over here as blue. And then there are intermediate matches for showing the kind of the matches that we're getting. So this whole work on a typical cluster of 100 CPUs and about having 2 gigabytes of memory took only like 4 days or more of whole compute hours on 100 compute memory. And then most of the people are not interested in copy number variations, but then this tool can find out the whole copy number variations. For example, for a particular loci in a chromosome, you want to know where the extra copies and to what percentage identity does it lie. You can also make a graphical representation like this. But of course, the graph looks very good, to look at, but you want to deal with actual data, so you would go back to the numbers. Okay, so this is a summary of the different structure variations. We have insertions, deletions, SNPs, inversions, and copy number variations. They are all, subcategorized into intrachromosomal and interchromosomal regions. Okay, so all these types of structural variations are then, mapped. And say, for example, if I have one individual, say Mr. Joshi, the name is very anonymous. He is put on the Y chromosome, and the UREF build 37, which is the latest one. I think build 38 is the latest one, but typically build 37 is the one which is being used. That is put on the X chromosome. And I'm putting a very stringent condition so that the similarity is at least 99.9% similar, right? So in that case, only most of the matches that I'll be getting will be along the diagonal lines, and there might be a few off-diagonal matches, which will be the copy number variations under very stringent conditions. So this is what I did for Mr. Joshi. Name is anonymous again. Mrs. Joshi, which is who is his wife, and they have 2 children, Ms. Kavita and Ms. Razia. All are anonymous names. So once we see the graphical output of what we are getting, because if you don't get a graph which is not what you would be expecting, then there's no point in looking at the numbers. The first thing is to look at the graph, see that the matches what you would have been expected using the model isn't compliant with what you would have expected, right? Once you've got that, you plotted it, you've seen what you wanted, and it is more or less what you wanted, it's not off the track what you expected, then go at the numbers, see at the various things. For example, this is a location of this net, and this is the alteration, and this is the flanking region up front of it, 10, 20 bases, this is after that, and then the minus sign can tell whether it is inversion or it's exact match, and there's some ID given to it. This was done for Mr. Joshi, he is Mrs. Joshi, Kavita, and Rabia. So these are the top 5 matches that I'm getting. There will be like lots of data like that. But just to see a snippet of the data, the results I'm getting, this is what you get. And of course, then you can filter out the columns that are not interested. For example, ATGCA. Once you understood what it is, then you can simply eliminate those flanking regions. And the best thing to do that would be to use R. R has a lot of statistical inbuilt tools like R SQLite. If you use SQL as a query language, R has an inbuilt SQL tool over there, so you can do statistical modeling along with database thing and do an integrated version of the same thing in a same framework. So you upload the data. It will come into picture when you do not want to use the data, right? So instead of having 10 data, you want to use just 3 of it and to see which one are the most important.
Like in one of your slides, you said that you have like more 80 GB of data and you just grab only about 640 MB of the amount.
Right.
So is it what similar to that kind of techniques only? What you have applied there?
So, are you taking sequences, like same sequences only for coding region or for engineering?
For the whole thing. But it can be taken for its own.
And how do you deal with that vocal sequencing where the column which for a particular coding, but the column which are varies, but they code for the same code, same amino acid. But the problem comes when the amino acid change. It also happens when the same physicochemical property of that amino acid which is altered. But suppose there is some change which alters the amino acid, and then it results into disease. Then how do you detect that it is a
So the change in amino acid is essentially dictated by the SNP. Some SNPs can be silent mutation, what we call about it. And then some SNP can result in a change in the amino acid. So that is taken care of by SNP. So all you have to do is put them in order and see a linear plot. The key lies, if I go back to the picture again, this is in a certain fashion, right? First chromosome, second chromosome, and then the Y chromosome, and then the mitochondrial. Similarly, your coding region should be also coded, put in aligned in such a way that it is in an ascending or descending order, so that you would already be expecting some kind of a linear plot like this. And if it comes somewhat different than this, then you can see how good your model is.